Jumping ahead in our textbooks again, we're now looking at Chapter 9, Section 2 for something called the Binomial Theorem. This is basically used to take a binomial that's being raised to a power and be able to expand it without sitting there and distributing over and over and over again. So it's a shortcut to make that process easier for you guys. So here's the purpose of using either Pascal's triangle or the binomial theorem. If you ever see these things used in the directions, mentioned in the directions, the idea is that you're just going to be taking some binomial raised to a power and then writing out all of the coefficients and then the variables raised to different powers. Now this expression here looks very complicated, but it's honestly not as bad as it seems, because you'll see that there are basically just three patterns going on at any given time. So the first number you see, if they give you something like x plus 2 to the 5th power, the coefficients p sub 0, p sub 1, p sub 2, p sub 3, etc., those are numbers that we're going to create from Pascal's triangle. And you'll see that on the next slide in just a moment. So you're going to learn a pattern to figure out which numbers to plug into those spots. The next pattern is going to be based on whatever you have in the first part of the binomial. So it's being represented by a in this case. Now the pattern for this is to start with whatever term you have here being raised to whatever power you have out here. So if our expression was something like x plus 3 to the 3rd power, then all you would be doing is starting from x to the 5th power and then counting down. So it would go x to the 5th, and then if you took that 5 and subtracted 1, you would have x to the 4th. And then if you took that 5 and subtracted 2, you would have x to the 3rd. And then you would keep going until you get all the way down to the point where you have x to the 0 power. So all that's being described with those numbers is it's saying start from the exponent you have outside the binomial and then count down for each term. So subtraction is all you need to do. And then something very similar is happening for the b term. So whatever you have in this spot, which for the example I'm showing right here is a 3, you would start from the 0 power and increase it until you hit whatever exponent you have outside of the binomial. So for this quick illustration here, you would start with 3 to the 0 power, and then you would be counting up. So now it says go from 3 to the 0 to 3 to the 1st, and then 3 to the 2nd power, and you would keep going until you got to the last number, which would be 3 to the 5th power. So wherever your exponent started from, that's where this term will end. It'll end with that same exponent there. So you're really just following 3 patterns. And like I said, I didn't fill in the coefficients for the p sub 0, p sub 1, p sub 2. You'll see where those numbers come from on the next slide here. So hopefully this Pascal's triangle here will seem familiar to you guys from Algebra 2. The idea is that you put 1s down the outside of the triangle, and then every time you have a pair of numbers, you add them up and write their sum in between in the next line. So add the numbers up, write the total there. If I added these two numbers up, 1 plus 2, that's where the 3 comes from. Same thing happens here, 1 plus 2, that equals 3. And then I have the 1s going down the outside again. So for the next row, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And then we can actually keep going here. So I wanted you to see that I can continue to fill in more and more rows based on which power of the binomial they ask me for. So I could go on to the 5th power, 6th power, 7th power, etc. So for the next row on Pascal's triangle, I would put more 1s down the outside of the expression, and then I would look at every pair of numbers I have in the row above. So 1 plus 4, if I add those up, that equals 5. 4 plus 6, add them up, that gives me 10. Here's another 6 plus 4, and then here's a 4 plus 1. So you will notice that there is some symmetry to it. You should see the same numbers on the left side that you see on the right side. So there should always be some kind of a pattern to see a lot of numbers getting repeated there. These are the coefficients that I was referring to on the previous slide for filling in that last part of the pattern. So you're going to create whichever row of Pascal's triangle you need, and that'll be based on the exponent they ask you for. So some important things to note about Pascal's triangle. The very first row is not the binomial to the 1st power, as some people expect. That first row is actually for the 0 power. So if I was asked to do something with the 4th power, you should actually be looking down at the 5th row of the triangle for which numbers to plug in. And then everything else, the pattern matches what I described to you guys earlier. So once you fill in Pascal's triangle coefficients, take the first term, which in this case is a, and begin with the power they have on the outside. So a to the fourth power for this one. And then the next term has a to the third, and then a to the second, a to the first, and then a to the 0, which you can just leave off because anything to the 0 power equals 1. B does the exact same thing, but it counts up instead of down. So it starts off with b to the 0 power, b to the first power, b to the second power, b to the third power, b to the fourth power. And it stops at the fourth because that was the exponent we had on the outside for that row. And then when you combine that with the coefficients from Pascal's triangle, 1, 4, 6, 4, and 1 for each of those terms, you just multiply whatever you have together. Sometimes there might be like 2 to the 4th times 3. So make sure if you have some constants that you go ahead and multiply them together to figure out what your answer would be. So now let's look at a couple of examples where we will apply this process on our own. It can be handy to have just a copy of Pascal's triangle next to you to use for reference, but I want to make sure you guys can also still create Pascal's triangle in case they ask you for rows that you have not generated before. So again, let's start with Pascal's triangle. You can write this out pretty quickly. You just put ones down the outside of a pyramid. And then remember, this is the 0 row, first row, second row. This is the third power. And then the fourth power, which is what I was asked for. So I can stop after I create this row here. For the first two rows, there's nothing to fill in. Once you get down to the third row, I have a 1 and a 1. So if I add those together, that goes in between in the next line. So 1 plus 1 is 2. And now I can go to the next row. 1 plus 2 is 3. 2 plus 1 is 3. That row's done. 1 plus 3 is 4. 3 plus 3 is 6. And 3 plus 1 is 4. So here we have the 0 power, first power, second power, third power, and fourth power, and that's the exponent I needed for our example 1 here. So now that I have these coefficients, I'm just going to go ahead and write them out, and I'm going to leave plenty of space between so that I can fill in my other numbers in a moment. So my coefficients are 1, 4, 6, 4, and 1. So looking back at what I gave you on the rule for Pascal's triangle and the binomial theorem, what we've just filled in is the p sub 0, p sub 1, p sub 2, and then we don't know how many terms there are for the general binomial expansion, but it ends with a 1. So we've just filled in those p coefficients, and then everything else is going to be based on what's inside of the parentheses. So now we're going to start with a to the n power and count down, and then b to the 0 power counting up. So looking at what a is, in this case it's an x. So I'm going to start with x to the 4th power for my first term, and then I'm going to count down. So x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and then this is x to the 0, but you can just leave that off because anything to the 0 power equals 1. And so then for the last piece, this b term is going to count up. So it's going to start with 2 to the 0, which I can leave off, and then 2 to the 1st power, 2 to the 2nd power, 2 to the 3rd power, and 2 to the 4th power. Now be careful with some of these cases. I want to make sure that I remember I'm multiplying 1 times 2 to the 4th. I don't want to accidentally think that that was saying 12 to the 4th power. So do make sure you understand that each of these parts for the pattern, these things are being multiplied together. And then between terms, I am adding the numbers. You may end up with some negatives if either your a or your b value is negative. So make sure you keep track of which signs are being raised to which powers in case that flips the sign on the whole term. But for now, these were both positive. So the last thing I want to do is just kind of simplify things. Instead of writing 1 times x to the 4th power, I can just write x to the 4th power. The times 1 isn't necessary. In this term here, I have 4 times x to the 3rd times 2. Well, the 4 and the 2 could be multiplied together. So I can instead write this as 8 x to the 3rd power. For the next term, instead of writing 6 times 2 squared, well, 2 squared is 4, and 4 times 6 is 24. So it's going to be 24, and then I still have the x squared there. On the next term, we have 2 to the 3rd power. So 2 to the 3rd power is 8, and it's 8 times 4 in this case, which is 32. And then this is the x to the 1st power term. And for the last one, we have 2 to the 4th power. So 2 times 2 is 4, times 2 is 8, times 2 is 16. And this one doesn't have any x's left. It was just the 1 times 2 to the 4th power part. So here we've expanded x plus 2 to the fourth power, and that was instead of sitting there and distributing out x plus 2 times x plus 2 times x plus 2 times x plus 2. Because the bigger the exponent, the more tedious and time-consuming that will become. So for bigger exponents, we use Pascal's Triangle or the Binomial Theorem. So now we're going to look at a more complicated example because my a and my b values for the binomial both have multiple parts on them. So a is 2x and b is 3y on this one. Before we start dealing with the a and the b, I'm going to fill in the coefficients for Pascal's triangle. So if we look back at the third power row, don't forget that it's the 0, first, second, third, and you can see that here on the left side as well. So the third power coefficients are 1, 3, 3, and 1. So I'm going to leave lots of space between my numbers. I'm going to have a 1, a 3, a 3, and a 1. And these are my separate terms, so I'll go ahead and fill in the plus signs here while I'm at it. So the coefficients came from Pascal's triangle. Now I look at what my a value is, which in this case is 2x, and I need to remember to start from the exponent on the outside, that's the n value, so 2x in parentheses to the third power. Now you want to use parentheses on this because I have to remember to apply the exponent to both parts of a. The exponent can be applied to both the 2 and the x separately according to our exponent properties. So 2x to the third power for the first term, and then 2x to the second power, 2x to the first power, and then this would be 2x to the 0 power, but I can just leave that off. For b, this one starts from the 0 power and counts up. So I'm going to have 3y to the 0 power, but I'm just going to leave that off since anything to the 0 power is 1. And then 3y to the first power, 3y to the second power, and finally 3y to the third power. So one of the things that makes this more complicated by having multiple pieces to your a and your b values is that the computations for your multiplications, there will be a lot more work to do on there. For this first one, I'm going to have 1 times, and the 1 times won't really affect anything, but I have 2 to the third power, which is 8, and I have the x to the third power. So the exponent's being applied to both of those pieces inside parentheses. For my second term here, I have several numbers that I'll have to multiply together. And make sure you follow your order of operations on this. So I want to do the exponent first. 2 squared is 4, and I need to multiply that 4 by the 3 here and the 3 here. All of this is in one term. So 4 times 3 is 12, times another 3 is 36. And x to the second power, y to the first power. And then I go on to the next term. So on this one, my exponent is for this last piece. So I have 3 squared, which is 9, times 2 is 18, times 3 is 54. And then it's x to the first power, since that was the exponent outside of this term. And for this piece, it's y to the second power. One thing you'll notice about the exponents on your variables is they always add up to be the exponent on the original binomial. So it was 3 and 0, which adds up to 3. 2 plus 1, which adds up to 3. 1 plus 2, which adds up to 3. And then you just keep going along like that. So here's the last piece. Now I have 3 to the third power. 3 times 3 is 9. Times 3 again is 27. Multiplying by 1 doesn't change anything. And it's y to the third power. So it will get kind of ugly when you have multiple numbers for the a and the b values. You just have to be careful about multiplying together those constants when you're working this out. Here's another type of question you'll see on many of the assignments. They're not going to ask you to expand the entire row. They're just going to ask you for one specific term. In this case, they want to know what is the term that has x to the fourth power in it if we were expanding x minus 2 to the sixth power. Well, for the first part, I need to create the coefficients for the sixth power. So we need to have Pascal's triangle handy. We didn't have this value worked out yet, so I'm just going to quickly fill in the ones down the outside. And then don't forget that this is the 0 power, 1st power, 2nd power, 3rd power. So 4th power, 5th power, and 6th power. When you're adding the numbers together, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then keep going down and filling everything in until we get to the indicated row for the question. And that's why, even if you don't have one handy, make sure you can fill this information in very quickly. So we needed the 6th power row, and here I have 0, 1st, 2nd, 3rd, 4th, 5th, and 6th. Now, if I think about the other information for the pattern, I know that the A value is going to start from the 6th power and count down. So I know that this would be x to the 6th, x to the 5th, and x to the 4th. So this is actually the most important part to me. I don't need all of the other terms. They're only asking me about the x to the 4th piece. So I'm going to write that the coefficient would be 15. And then since a to the 4th power is x to the 4th, the other value is going to be counting up for the exponent. So I know it would be -2 to the 0, -2 to the 1st, -2 to the 2nd. And I also could have determined that by knowing the exponents for a and b should add up to the number on the outside. So since I knew this one was a 4, I did know that this one was going to be a 2 as well. All I have to do is this one computation now. We're not going to waste our time computing all of the rest of it. -2 times -2 is 4, and 4 times 15 is 60. So we found the x to the 4th term because I have x to the 4th power in my expression right here. And what they really wanted to know was the coefficient, which I now know is 60 after I combined everything from a, b, and the Pascals Triangle coefficient. So hopefully all of that will be helpful. That way when you get to the test on this unit, you won't find yourself being asked to expand something and just write them farther and farther apart. The expanding is that act of actually multiplying out your powers. And we don't want you to do it by sitting there and using the distributive property over and over again. We want you to use this Pascal's triangle and these shortcuts so that you can get through the questions faster.